Hi everybody, this is the Unit 1P test review, and these are the things what will be on that test. We're going to go over Chapter 2 and 3, forces and directions, equilibrium, Copernicus, Newton, what a Newton of force is, distance and displacement, the Moving Man Virtual Lab, the Hot Wheels Track Data Lab, time, speed, distance calculations, and then finally Newton's laws of motion. So this will be on the exam. Tomorrow we'll have our live discussion, which will be Thursday, and you can get on the video conference. We can answer any questions you have. When you finish going through it, just watch this. There's no assignment with it. Go back and any assignments you have you need to do those. Do that also on Thursday. The test will be up Friday. You can take it anytime you want. You'll have about an hour, 10 minutes to get it done. And that's how we'll work it. Alright, first things first. And our first thing is the Unit 1 test review of force. And force is a push or a pull, and it will change an object's state of motion. Now, that is, if the force is strong enough to overcome the inertia of that object. Net force is all the forces acting on an object. Most of the time there are more than one force, there's more than one force working on an object. When these acting on an object are zero, the object is at rest. It is either still or motionless, or it's still or motionless. A vector is simply an arrow, and it has magnitude and distance. These are the magnitude is distance, same thing when they talk about magnitude, and then direction. So a vector has these two things. Direction does not present distance, and then a simple line doesn't. So a vector is what we talk about. It's used all the time in aviation. And here we go. Now, a vector will have a point of origin. The point of origin is at the end. It's usually a dot or a point. And then there will be a length to that vector. And at the end of that length there will be an arrow. That indicates the direction that the vector is moving. So it has a point of origin. The end of the arrow is the point of termination. And this line that forms between those two things, that's the distance, and that is the direction of the trajectory. A trajectory is a movement of a projectile. This is the compass rose. You're going to need to know about that. The compass rose, and this is pretty simple. Most of you have seen this. You start in the middle at your point of origin, and then to the top of a page is north, to the bottom is south, to the right hand side of your page is east, to the left hand side is west. Those are the four cardinal directions. The secondary directions are the diagonals between these cardinal directions. So if you are on the diagonal of north and east, it is northeast. If you're on the diagonal of north and west, that is northwest. If you're on the diagonal of south and west, it's southwest, and then southeast is down here. We'll go to that. You'll do some more. You'll have quadrant 1, 2, 3, 4 in math. I don't think we get to that with what we do. All right, equilibrium. Mechanical equilibrium. Let me get my paper down here where everybody can see it. There it is. Mechanical equilibrium. That is readiness where no physical changes can occur. A drag car can be sitting at the starting line and it is ready to move. It's got a lot of tension on it, but it is still in equilibrium. It's just ready to go. When they let off the brake or dump the clutch, away it goes. But this is equilibrium. Equilibrium does not show movement. It simply is a ready state. An object cannot be in equilibrium under the influence of only one force. So if you only have one force acting on an object and it's enough to break inertia, that object is going to be moving in a direction. Copernicus. Copernicus was the Polish astronomer. He determined in his heliocentric model of the solar system that the Earth was not the center of the solar system, it was the sun. This was a very big deal. He places the sun at the center, not the Earth. The church is in control at this time, and they do not think that God, the Creator, would put anything other than his greatest creation, which was Earth, at the center. But that's not what he was finding. He did have a problem, though. He couldn't get the math to work because the path of the planets do not form circles. They don't go straight around, they form these ellipses. And you have to have calculus to calculate those accurately. And it was not invented yet. That was invented by Newton later. Copernicus, he worked in secret because he didn't want to be persecuted by the church who had the power, and they would certainly do that. All right, Newton. We've all heard of Newton's laws, and we study them all the time. That's what we're doing right now. He wasn't a great student. He moved back home to his mother's farm. He was sent off to school, and he came back home to avoid the plagues. The plagues were going through Europe, and I'm to hold my head kind of funny. I got this GoPro thing on, and it's I don't have it, so that's a little better there. Okay, that's better. So he solves problems while he is avoiding the plagues of Europe. And he solved them by continually thinking about them long and hard. Where are we at? Okay, I need to be over here. That's a little better. So he solves them by thinking long and hard, not by sudden insight. And a lot of people think you have these eureka boom all of a sudden, which is called insight. And a lot of people say you're touched on the brow by God and develop an understanding. That's not how Newton felt like he learned and solved problems. He spent a lot of time on them. A lot of creative people will tell you this too. Mass is the amount of matter in an object. Weight is a measurement of the force on the body. That's gravity. Okay? Mass and weight are not the same. They are not interchangeable. A newton of force is the amount of force needed to move 1 kilogram, an acceleration rate of 1 meter per second, which is a little more than a yard. Okay? So you're moving it at a rate of at 1 kilogram. You're moving at 1 meter every second, and it increases per second, so that's second squared. A newton of force is slightly less than a quarter pound of force. So it's about a cooked quarter pounder, because a quarter pounder is a quarter pound before cooking, and after you cook it, it doesn't have a quarter pound. So it's going to be about a newton. So you might ask them for a newton instead of a quarter pounder, and I'm sure they'll throw you out. But anyway, that's okay. All right, 1 kilogram object will weigh about 10 newtons. And that is it for chapter 2 and 3 text. Moving on. All right, we need to talk about the difference in distance and displacement. Distance is how far you travel. That's the path that the object takes. Displacement is how far the object is from the point of origin, that's where you started, when you finish or stop, when the path's complete. So if you walk 10 miles and you stop where you started, your distance is going to be 10 miles. We walk this 10-mile path. We return to the start. Our displacement is 0. And this is our point of origin right here. Okay? And physics deals with displacement more than distance. We do more with displacement. All right, the Moving Man Lab. We're going to do some problems with that. We'll do some little exercises. Let me make sure I'm moving in the right direction. Okay, we got you in here. There we go. So, if you move at a constant rate of 5 meters per second, for 4 seconds, how far would you move? That one's not hard at all. So, you're moving at 5 meters per second. We go for 4 seconds. 5 times the 4 is 20. Easy enough. If the man begins on the 0 mark of the following illustration, this is like the lab that we did, and you move for 2 seconds at a rate of 5 meters per second to the east, you're moving east, and then you travel west for 3 seconds at a rate of 5 meters per second. 2 questions. Number 1, what's the distance? And number 2, what's the displacement? So, if you start at 0, 0 is here, and we go for 2 seconds at 5 meters a second, we're going to go 10 meters, and that's to the east, and that's what this arrow shows, and that's what the line is there. On your test, there will probably be a wall there, and you could only move, if you're moving 5 meters per second, you could only move 2 seconds. If you go any farther that way, you won't go any farther because you'll hit the wall or stop at the wall. It then says he turns around and he goes to the west at 5 meters per second for 3 seconds. So where does he end up? He ends up at -5. His total displacement, which is b, that's 5 meters, because if you begin at 0 and you stop back here at -5, your displacement is 5 meters. Your distance, you went 10 this way and then 15 back the other way. So that's going to be 15 and 10 is 25 meters. I'll probably change some units on you, so be careful about that. Come on, paper. I know there's another one back behind there. There it is. Okay. Which is probably what we're going to do here for a minute. Let's look at these for just a bit. You have a rate of 5 meters a second again. That's good. And for 2 seconds, then you accelerate to 20 meters per second for 4 seconds. Then you decelerate to 10 meters per second for 5 seconds. And here are our 2 questions. Number 1, how far did you travel? And number 2, how many seconds did you travel? So the first one, you went 5 meters per second for 2 seconds. That's 10 meters. The second one, you accelerated to 20 meters per second for 4 seconds. That's 80 meters. And then you go 10 meters times the 5 seconds is 50 meters. You add those up, you get 140 meters. Okay? How many seconds did you travel? The first section, the first velocity you were at was 5 meters per second for 2 seconds. Then you went for 4 seconds. Then you went for 5. So 2, 4, and 5 is going to be 11 seconds total. And you'll have questions like that. I may try to put that graph on there. I'm not sure if I can. You know, the one with the 3 graphs, and see if you can interpret the graphs. If I can get that on there, good. If not, we won't do that. And that's just, I don't know what else to do with it. My clipboards are flying all over the place here. Let me get this one. Okay. The Hot Wheels track. This is the Hot Wheels track data. Remember how we did this? I'm going to put this on there. And then you will be given the mass of some objects, your stopwatch reading, and then I will give you, you're going to calculate the readings on the stopwatch in centimeters per second and also in miles per hour. And we did this in the lab, so you should be able to do that. Shouldn't be too bad. We'll also do some PhotoGate readings, and in those PhotoGate readings, see if I can get it right. You'll be given the seconds for the PhotoGate reading, and that's the final velocity or the final speed. They're 20 centimeters apart, so you're going to have to take 20 and divide it by the reading. That's what you're going to get right here, 287.365 in this case. You take the average, you divide this by 2. That's where this number comes from. And then your average speed in miles per hour, you multiply what you get here by 0.002. That'll give you miles per hour. And I'll ask you some questions about those. I'll give you 5 objects over here. You'll do some calculations, and I'll ask you what the average speed in miles per hour are for the steel ball or the glass marble. So we'll have 3 or 4 things, or the car. Okay? We'll also have the 35-degree track and the 25-degree track. And you've done those. If you need some help with that, you can ask on Thursday. Time, speed, distance. These are not too difficult. We can do these. Distance is equal to speed times the time. A dot between 2 things means you multiply them together. If you travel 50 miles an hour for 2 hours, how far did you travel? 50 times the 2 is 100 miles. If you travel 50 miles an hour for 4 hours and 15 minutes, how far did you travel? The 15 minutes you'll need to remember is 0.25 hours, or a quarter hour. Use the decimal. You're traveling at 50 miles per hour. You're going to do that for 4.25 hours. You do the math on your calculator, 212.5 miles per hour. You can use your calculator on your exam. Now, if you put speed and time at the bottom of the triangle, remember up here we show speed as time, speed times time is distance. That goes at the bottom of this triangle, and then you put the D at the top standing for distance. To find what you're looking for, you simply cover what you're wanting to look for. For instance, if I want to look for distance, I cover it. What's left is speed and time down here, and I'll put a dot between them. It makes it easier. So speed times time equals distance. If I want to figure out time, I can cover up time, and I've got distance divided by speed. If I want to find speed, cover up speed, and I can do distance divided by time, and that gives me the speed. And that's the 3 calculations, or the formulas that you see at the bottom of this page. See them down there? Distance, speed times time. Distance is speed times time. Speed is distance divided by time. Time is distance divided by speed. And then 3 examples. Your car's traveling 1,000 miles at a constant speed of 60 miles per hour. How long would it take to travel 1,000 miles? Time is down here. I cover it up, and I've got distance divided by speed. So 1,000 divided by 60 is going to leave me with 16.6 hours. The second one, a car travels at a speed of 100 kilometers per hour for 30 minutes. How far did the car travel? Distance, I cover that up, so I've got speed times the time. 30 minutes is half an hour. So if I'm going in kilometers per hour, I've got to do the 100, that's the speed, times the half hour. So I'm going 50 kilometers. 50 kilometers in a half hour. Okay? And the last one, car travels at 100 miles in 300 minutes. What was the average speed in miles per hour? There's 60 minutes in an hour. 300 minutes divided by 60 will give you 5 hours. Speed is down here. I cover it and I get distance over time. I go 100 miles in 5 hours. I'm doing about 20 miles per hour. That's it. So there'll be some of those on there. Speed, time, distance stuff. Last section, Newton's laws. He's got 3 laws, and they are, okay, let's get this done up here. Going the wrong way. That's better. All right, his first law, every body or object remains at rest or constant motion unless it's acted on by an external force. This is the law of inertia. Everything on Earth is acted on by gravity, so there is a force. The 2 big forces are that and then friction. That's 2 of the big forces on Earth. The second law, an acceleration is directly proportional to the force, and then it is inversely proportional to the mass. Directly proportional means as one thing increases, the other thing increases. As the force increases, the acceleration will increase. When one thing decreases, the other decreases. That's directly proportional. Inversely proportional is one thing will increase, the other decreases. As mass increases, your acceleration decreases. When one thing decreases, the other increases. As mass decreases, velocity increases. So that's the second law. All right, last page, crew. Third law, for every action, there's an opposite and equal reaction. You can only push on an object as hard as it can push back. When it can't push back anymore, you knock it over, or a different force is applied to that object. You're applying more force than it is. So now we're unbalanced. Unequal forces produce movement. Acceleration and force are directly proportional, and acceleration and mass are inversely proportional, meaning as one goes up, the other goes down. So that's going to be about it for this exam. What you need to do is just watch this. You may watch it a couple times. Watch it once today. Watch it again tomorrow. If you have any questions, you can ask me on our video conference call, and I'll have that up on the calendar. Be sure you get all your past lessons done, and then Friday we'll have the exam up, and you'll be able to jump on. You'll get 1 attempt, and you'll get about 1 hour and 10 minutes. All right, guys. See you tomorrow.